Okay, in this video lesson, we'll have more example of related rates or time rates in calculus. So the first problem. Okay. One leg of a right triangle is always 6 centimeters long, and the other leg is increasing at a rate of 2 centimeters per second. Find the rate of change of the hypotenuse when it is 10 centimeters long. Now, remember that one leg is always 6 centimeters, so let's have this as that constant leg. So it's always 6 centimeters. So it means that this leg here, let's denote it as x, and the hypotenuse of course as h. So these two variables, x and h, will change. So you're given the rate of change of the other leg, so we're given dx over dt, and that is equal to 2 centimeters per second. And we are asked to find the rate of change of the hypotenuse. We have to find dh over dt. Now, the challenge really in related rates problem is to find the equation relating the variables involved, which in this case is very obvious because we have a right triangle. So this is a right triangle. So it should follow the Pythagorean theorem, and it is x squared plus 6 squared equals h squared. So once we have the equation, the next thing to do is to differentiate all the variables involved implicitly with respect to time. So differentiating each term implicitly with respect to time, 2x squared will give 2x times dx over dt plus 6 squared is a constant, so the derivative must be 0. And h squared, the derivative would be 2h, and then dh over dt. Now that we have the equation relating the rates of each variable, we simply plug in what are given and solve for the known. So dx over dt is given, that's 2 centimeters per second, equal to 2 h times dh over dt. Now, what should we put here? X. So in the given, the hypotenuse, find the rate of change of the hypotenuse when it is 10 centimeters long. Therefore, at that moment, h is 10 centimeters. So we should put here 10. And what is x? At that moment when h is 10. So x must be x squared plus 6 squared equals h squared. Therefore, x squared plus 6 squared equals 10 squared. That will be 100. So x squared is 100 minus 36 or 64. So you get x squared of 64 or 8 cm. So you should put here 8. Now notice that we can now solve for dh over dt. So 2 times 8 times 2, that would be 32 centimeters per second is equal to 20. So that's 20 times dh over dt. Now solving for dh over dt, which is the rate of change of the hypotenuse with respect to time, we get 32 over 20 when simplified would be 8 over 5 centimeter per second. Done. Now let's go to the next problem. At a certain instant, the length, width, and height of a rectangular parallelepiped are 3, 4, 5 inches, and they are increasing respectively at the rates of 2, 4, and 6 inch per second. At what rate is the volume increasing? Now, so that we know what is happening, let's say this is our parallelepiped. And all the dimensions are said to be changing. So let this be the length, this be the width, and this be the height. Remember that all the variables, the length, the width, and the height, are changing by this rate, 2, 4, and 6 inch per second. So after some time, this parallelepiped must increase. So let's say like that. So it is increasing. It's obvious that the volume is also increasing. So therefore, we should come up with an equation relating the rates of change of the volume with the rates of change of all the dimensions. Now, let's start with what we know. We know that the volume of a rectangular parallelepiped is length times width times height. Now, we have the equation. So we proceed to differentiating the equation implicitly with respect to time. Now, the problem is there are three variables in the right side. So we should apply power rule, grouping the first two terms first. Let's group L and W first before differentiating times H. So now we can now differentiate implicitly with respect to time. What's the derivative of V? You know, it's dV over dt. Again, with respect to time. Equal to, now we have a product on the right side, LW and H. So copy LW and times the derivative of H implicitly with respect to time will give you dH over dt. Plus, copy H and get the derivative of LW, which happens to be a product again. So you have to use the power rule again. So copy L multiplied by the derivative of W implicitly with respect to time gives you dW over dt plus copy W and the derivative of this should be a quantity. So remember, copy H here and the derivative of the product. This is the product. We started with copying L and getting derivative of W implicitly with respect to time, dW over dt, plus this time copy W and derivative of L will give you dL over dt. Now let's simplify this equation that will relate all the rates of change. dV over dt is equal to LW times dH over dt plus, now distributing H, so you have HL times dW over dt plus HW times dL over dt. Now, we have the equation involving all the rates of change. So all we need to do is substitute all the given. So we have the rates of change of this 2 here is the rate of change of the length. So you have here 2. This 4 is the rate of change of the width. So you have here 4. And 6, the rate of change of the height. So it's respectively. Now, what are the dimensions at that moment? So we have L at that moment. So length, width, and height are 3, 4, and 5 inches. So let's just write them. L is 3, W is 4, H is 5. And plug it in. So you have 3 here, 4 plus H is 5, L is 3 plus H is 5, W is 4. And just do the math. 3 times 4, 12 plus 6 times 6, 72. 5 times 3, 15 times 4, 60. 20 times 2, 40. So This all adds up to 172. And the unit, of course, would be inch cube per second. So this gives us the rate of change of the volume with respect to time, given the others. That's it.